So an ideal fluid has a laminar flow, which means that the velocity of the fluid at a given point in space is not changing in time. And it's also incompressible flow, which means that the density of the fluid will not change as the fluid flows. It will not compress. So same mass will have same volume, right? Non-viscous flow, which means that the fluid will flow freely. There are no losses from friction. And finally, it's irrotational. It means it has no turbulence. So this image will show us what is laminar flow. Laminar to turbulent flow, and definitely turbulent. So laminar, you can actually see it's like moving very, very steady. Then you can see, for instance, smoke. We have laminar flow at the bottom part, and as it rises, it starts to become turbulent. And turbulent means it has no actual. It's very, very messy, right? It's a mess, okay? And in order to work with these kind of fluids, first we have some equation which is called the continuity equation. And this continuity equation is going to be due to the conservation of mass. Mass is conserved. So for instance, if we start here and we take any given part of the fluid at the entrance of this pipe or whatever, we have there a change in x dimension, which we know is velocity. So this is x1, velocity 1 times a change in time. Now this also has a change in mass, okay? This is a part of mass, very small part of mass, and it's going to be equal to density times volume 1. Density is constant, it won't change. And of course, if we change volume, in this case, it's going to be area 1. So we conserve density, area 1, changing 1. There's no minus, there is an equal to. Questions? It happens exactly the same at the right part, which means at the very end that density area delta x1 is going to be equal to density area delta x2, and we know that this is area 1, this is area 2, they change, and we understand that we can cancel density with density because the density remains constant, and at the very end we're going to have area 1 delta x1. So delta x, we can change it by velocity times time, which means it's going to be area 1 velocity 1 delta t equals area 2 velocity 2 delta t. And since it's happening in the same time, we can cancel times and we get to the continuity equation, which is area 1 velocity 1 equals area 2 velocity 2. As mass is conserved, energy is conserved as well. We can actually see this diagram, and we know from the beginning that work is going to be equal to minus a change in energy. If energy is changed, it means a work has been performed. And we know that work is going to be force times displacement. So in any given part, left part, right part, we know, or we can actually state that work is going to be equal to the force times the change in displacement, which happens at part 1, minus force times a change in displacement, which happens at part. Now we know that force in this case is due to pressure, and it's pressure 1 area 1 delta x1 minus pressure 2 area 2 delta x2, and we can actually conceive area times delta x as volume, which means then this is going to be pressure 1 volume 1 minus pressure 2 volume 2. So we can actually understand pressure times volume will give me work. If we equate this to the kinds of energy that we can actually have, which energies can we actually have? So we can equate them to the energies which are kinetic and potential. We can actually state that pressure 1 volume 1 minus pressure 2 volume 2 is going to be equal to a change in kinetic energy. Since we have a minus change, it's going to be final minus initial, so it's going to be mass 2 gravity height 2 minus mass 1 gravity height 1, which is the potential, and we're going to have as well kinetic plus 1/2 of mass in the section 2 velocity 2 squared minus 1/2 of mass 1 velocity 1 squared. Is it okay? Since mass is conserved, volume should be the same one. We can actually factorize volume, pass it to the other side dividing, and we have in every term mass over volume, which is the density. So we can actually state this is pressure 1 minus pressure 2 is going to be equal to density gravity height 2 minus density gravity height 1 plus 1/2 of density velocity 2 squared minus 1/2 of density volume 1 squared. It is the same volume or the same volumetric flow due to the continuity equation. The continuity equation actually area 1 times velocity gives me the volumetric flow. So the volumetric flow, which is the amount of volume per unit time, is going to be equal to area times velocity. So in these equations, which is the conservation of energy, since we have the same volumetric flow, it's the same volume at both parts over the mass, it gives me the density. That's per unit time. Finally, we can express this equation as pressure 1 plus density gravity y1 plus 1/2 of density velocity 1 squared, which is the term of pressure due to work, density gravity height, which is due to potential energy, 1/2 of mass velocity squared, which is the kinetic energy, is going to be equal to pressure 2 plus density gravity y2 plus 1/2 of density velocity 2 squared. This equation is known as Bernoulli's equation, and is just a conservation of energy. Is it okay?